So in the second video on section 4.2, looking at the graphs of logarithmic functions. So just like we did with exponential functions, we're going to graph these to begin with just using transformations, which means that we need a basic shape to work off of. So the basic shape that you have on your screen is the basic shape of log base b of x, where b is bigger than 0 but not equal to 1. So we want to recognize a few characteristics of this graph that we're going to use in our transformations. So the first thing to point out is the one significant point that we'll move and use to help in our graphing, and that's the x-intercept of this basic shape, which is located at 1, 0. The other characteristic that we want to recognize is the fact that a logarithmic function has a vertical asymptote. And in the basic shape, that vertical asymptote is located at x equal to 0. Now remember, a vertical asymptote always has to be written as an equation because it describes a vertical line, so it should always be x equals. And we'll talk a little bit more about that in just a minute. So those are the two characteristics that we're going to use in our transformations. So based on our shifting and reflecting, we're going to move that one point and that vertical asymptote. Now a couple of other things over here that we want to identify are the domain and the range. I've already talked about the vertical asymptote. So let's talk about the domain. Now logarithmic functions are going to be another function that you have to add to your list of functions that have restrictions or may have restrictions on their domains. So we've already had rational functions where we had to pull out restrictions on x that made the denominator 0, and we also had square root functions where we had to make sure that whatever was underneath the square root symbol was always greater than or equal to 0. In a logarithmic function, we always have to make sure that the argument of my logarithmic function is strictly greater than 0. You cannot take a log of a negative number. So when you're looking at this graph, you can see that I'm forcing the argument of this basic logarithmic function to not be negative by that vertical asymptote, because the entire graph is to the right of x equal to 0, forcing every x to be positive. So in this basic shape, my domain is going to be from that vertical asymptote of 0, but then it does go to the right forever. So it goes from 0 to infinity. And they're both going to be closed with a parenthesis. Infinities, of course, are always closed with parentheses. And the 0 is closed with parentheses because this branch to the left of my x-intercept is getting closer and closer to that vertical asymptote, but will never cross the vertical asymptote. Whereas the branch to the right of that x-intercept is continuing to the right forever. It is also continuing to rise forever. It just kind of does it at a very slow pace. So that means that my range, if you look at how low, how high my graph goes, it does go down to negative infinity, and it does continue to rise to infinity. So my range is all real numbers for any logarithmic function. Okay, now I want to do a couple of examples where we look a little bit closer at the domain. We've already talked about finding the domain from the graph of this basic shape of a logarithm, and you can see that my x values have to be strictly greater than 0. So the thing that you want to remember when you go to find the domain of a logarithm algebraically is that you cannot take the logarithm of a negative number, nor can you take the logarithm of 0. So that means that the argument of your logarithm must always be strictly greater than 0. So once we set up that inequality, we're just going to solve for x, and that will give us what our domain is. So I've started with number 19. I don't know where 1 through 18 went, but we're starting with number 19. And we want to find the domain of the log of x minus 4. So I want to just follow these two steps. I want to set the argument, which is x minus 4. Remember, the argument is what you're taking the log of. And I want to force that to be greater than 0. Now, I'm not mentioning at all what the base of that logarithm is. This one is base 10, but it would not matter if my logarithm was base 2 or base e. I would still be following the same steps to find the domain. So for the domain, you just focus solely on what that argument is. So when I solve for x, I get x is strictly greater than 4. So in inequality notation, there is my domain. And in interval notation, I can choose any x as long as it's in the interval from 4 to infinity, not including the 4. So I need that parenthesis by the 4. Okay, if you want to stop the video and try number 20 on your own, and then we can check to see if you got it right, that would be a good time to do that. So on number 20, we've got the natural log of 3x plus 1, and we want to find the domain there. And again, this time my base is e, but that doesn't change the steps in finding the domain. So I want to take the argument, which is 3x plus 1, and I want to force that to be greater than 0. When I solve for x, I'm going to subtract 1 and then divide out the 3. So x is greater than negative 1/3. So there's my domain in inequality form. And in interval notation, my domain would be negative 1/3 to infinity. So I can choose any x as long as it is strictly greater than negative 1/3. So we're going to need to find these domains, particularly when we get to equations, because we're going to want to make sure that the answer we get for x, or the value we get for x, is allowed based on the restriction for the domain. So just remember the two steps. Make sure the argument is greater than 0, and then solve for x when you're finding the domain algebraically. Okay, so let's get back to the graphs of logarithms and take a look at a couple of examples where we do transformations. So when it comes to doing graphs using transformations, the first thing that I want to do is identify what the transformations are. So the first thing that I notice is that I've got plus 1 directly on my x. So remember, values being added or subtracted to x are my horizontal shifts. So this is going to shift my graph to the left 1 unit. And then I've also got the minus 2 on the outside of the function. So adding or subtracting outside is a vertical shift. And in this case, we're going to shift my graph down 2 units. Now, again, I'm not pointing out the base. When it comes to transformations, what the base of my logarithm is not going to affect how I draw my curve. So don't worry about the base, just worry about what's being added, subtracted, and any negatives for reflections. So we're ready to sketch this curve. So remember, the two things that we want to move are the x-intercept, which is normally at 0, 1, and the vertical asymptote, which is in the basic shape at x equal to 0, or the y-axis. So let's start with that vertical asymptote. Now remember, asymptotes, a vertical asymptote will not be affected by reflections, nor will it be affected by vertical shifts, but it will be affected if I'm shifting left or right. So this one has a shift to the left 1 unit. So I'm going to shift that vertical asymptote 1 unit left, putting it here at x equal to negative 1. Now I'm going to start with that point. My point is normally here at 0, 1, I'm sorry, 1, 0, and I want to move that to the left 1 and down 2. So if I go to the left 1 and then down 2, that puts my point here at 0, negative 2. And that's all I need is that vertical asymptote and that 1 point. And now what I want to do is just copy that basic shape. So remember what that basic shape looked like for a logarithm. And we're just going to mimic that here in this one and sketch my curve like this. So there's the graph of my logarithm using transformations. Now, a couple of things that we might want to pull from this, a couple of questions you might be asked is where the vertical asymptote is and what the domain and range are. So I've already listed here what my vertical asymptote was. So let's talk about the domain and range. Now, let's do range first just because that's easy for logarithms, because my graph goes down to infinity and up, down to negative infinity and up to infinity. So my range is negative infinity to infinity. And now the domain. When we're doing transformations, you have two options for doing the domain. You can do it algebraically from the formula of the function, or you can do it by looking at the graph. I'll show you both, and you just pick whichever one you like better. So if I do the domain algebraically, remember that means setting the argument strictly greater than 0. So the argument of this function is x plus 1. That's what I'm taking the log of. So if I force the argument x plus 1 greater than 0 and solve for x, I get a domain in inequality form of x greater than negative 1. So that would be in interval notation, negative 1 to infinity. Now you can also see this from the graph, because if you look at how far left and how far right the graph goes, it goes as far left as that vertical asymptote at negative 1, and then also goes to the right forever. So my domain is negative 1 to infinity, and again you can look at it graphically or algebraically, whichever you find easier to do. You will have to know how to do it algebraically when we get to equations. You don't want to have to graph the function every time just to figure out the domain. So know both ways. Okay, one more quick example of a graph, this one with a reflection in it. So if we identify what the transformation is, we can see we've got this negative in front of the x, which means that that is going to be a reflection, and it'll be a reflection through the y-axis. So a negative in front of the x is going to flip it left, right, so to speak. It's going to make all of my positive x's in the basic shape negative and any negative positive. So let's take a look at what that graph would look like. So if we start with the vertical asymptote, remember vertical asymptotes are not affected by reflections. So that means the vertical asymptote is staying at x equal to 0. And then if we look at that point, which is in my basic shape at 1, 0, if I reflect that through the y-axis, think about folding the graph along that y-axis. The point would end up in its mirror image on the other side of the y-axis at negative 1, 0. And then what I want to do is think about the shape and how that's going to be reflected. So if you think about what the shape is in the basic shape, let me just sketch it in here, just a little bit of it. So in yellow there, that's what my basic shape usually looks like, but I want to reflect it over that y-axis, which means that these points here are going to be here, and these points that were normally heading to the right are now going to head to the left. So overall, what my curve would look like would be like this. So it just flips everything over, reflects over that y-axis. So now if we identify the vertical asymptote, I already have that listed here. And then if we do our range first, just because that's the easy one, is all real numbers. And then our domain. So again, let's look at this algebraically and graphically. If I do it algebraically, I would set that argument strictly greater than 0 and get x alone, solve for x. So to solve for x, think it through as getting rid of that -1 in front of the x and dividing by -1 on both sides, which would give me a positive x on the left, and I would keep 0 on the right. But remember the rule that anytime I divide by a negative number, that flips the inequality sign. So in inequality form, my domain is x has to be less than 0. And you can also see that in the graph. Remember, the domain is how far left, how far right. So notice this curve goes to the left to -infinity, and it goes to the right up to that vertical asymptote. So my domain, whether you do it algebraically or graphically, is going to be -infinity to 0. So now you should be able to finish all of your 4.2 homework between this and the first video on logarithmic functions. If you have any questions, make sure you email me.